And the cakes? Yes? Okay, so we can start. Second level. It's resistant thermometers. This is a picture about, mostly resistant thermometers used in power stations, chemical, petrochemical industry. Most of it. So, for resistant thermometers, we also have some subdivisions, which is given here. Standards and definitions, sensing techniques, thermometers, material, wiring, measurement uncertainty, dimensions, and some special applications. So materials increase their resistance with temperature while decrease their conductivity accordingly. Everybody knows it. Conductivity is based on the movability in the electrons in the valence band of the conductor. The oscillation amplitude of the atom in the crystal structure increases with temperature. The crash between valence electrons to the outer electron shells of the atoms and their disturbance increase the statistical average and leads to the thermal dependent increase in resistance. The specific thermal increase of the resistance is named temperature coefficient, and it is normally nominalized by the Greek letter alpha, which is the first character in the Greek alphabet. It is a material-specific parameter, and for metals, normally positive. Only some exotic alloys used in furnace manufacturing have positive and then partly a negative coefficient and then again a positive temperature coefficient. Some modifications of graphite have a positive and negative effect. It depends on the temperature range and the crystalline structure. So graphite is an exception from it. The relationship between temperature and resistance is nonlinear and is described by a polynomial expression of a higher degree. So this is a small selection of materials with their resistance coefficients in 1 per Kelvin. And you see most of the pure metals are in a small range between somewhat around 4 and 6.5. You see mercury is an exception with 0.9, but all the others are in a quite small range of numbers. Alloys are different from it. They have a wide range. It depends on the kind of alloys. And non-metals, you see carbon and graphite, they have a negative temperature coefficient. Semiconductors, well, they are outside because semiconductors, because of the composition, you can assign it to any resistant coefficient, either positive or negative. So semiconductors are really seldom used for temperature measurement. Okay. Two groups of resistant materials are different in case of their specific pitch. This is NTC and PTC resistors. NTC is negative temperature coefficient, PTC is positive temperature coefficient. Most resistant thermometers containing a metal are PTC sensors. The so-called calendar-van Dusen equation for platinum RTDs is a polynomial expression of the third degree, and there are, as mentioned by the degree, 3 coefficients used, A, B, and C, and the complete range is subdivided in two parts. For the range of minus 200 to 0 degrees, you have to use all the three parameters as given in the equation. And for the range of 0 to 850 degrees, it is reduced to only two parameters, because the linearity above 0 is much better than the linearity below 0. The same happens with the sensitivity. The sensitivity of a platinum resistor above zero is better than below 0, and decreases close to 0 when you come near to the triple point of hydrogen. The sensitivity in this range is very, very low. Okay, this equation is not usable for very pure platinum sensors, as they are used in standard resistance thermometers for scientific use. Yes, this means that for such thermometers the alpha value is slightly higher. The theoretical alpha value for 100% pure platinum is 893. 0.000893. And you can achieve 925, 926. This is possible. And when you compare it with the alpha value for industrial thermometers, which is, as you know, 385. 3851, of course. Then you see that there are some impurities in this industrial platinum, and this, when you use such alloys, such platinum with such impurities, then the Callendar-Van Dusen equation applies. Okay, the sensitivity in ohm per Kelvin is given with the same coefficients, but a different formula, of course. And for a small positive temperature range, you can also further on reduce the formula, so it is easy to do it. But in our time, nearly everybody has a smartphone or a tablet or even a PC on his writing table, so it is not a question any longer for have a look in tables or calculate by hand such formulas. Okay. The accuracy for platinum resistant thermometers are in accordance to IEC 751. It has no change. It has get a 60 before the 751, so the newer edition is called IEC 60751, and it is subdivided in two major classes. They have a third class, but they are now subdivided in two classes. Class A, sometimes also mentioned as class 0.15, means the accuracy or the permitted deviation is 0.15 or plus, no, 0.15 plus 0.002 times temperature without pre-sign in degrees centigrade. Yes, the absolute value of temperature in degrees centigrade. And class 1 is roughly double of it. Okay? This is an international standard. And as far as I know, it is also valid here in India. Okay. There are, beside platinum, also other materials available and partly in national standards also standardized. For example, copper. Since, let's say, nearly 2000, copper-resistant thermometers in North America and in Europe are mostly used for monitoring the ball bearing temperature in steam generators, in steam turbines, and in the big generators behind it. Yes. Now it has changed in the meantime, but from time to time my previous company got inquiries for copper thermometers, and it became more and more difficult to get the material for it. The temperature coefficient is close to platinum. This is a disadvantage. We come later on back to it. Nickel is used, it's rather linear and with a higher temperature coefficient, but only in a limited range. And again, nickel is also possible to do it in the same process as to produce semiconductors or controllers. Nickel-iron alloy, basically the same as pure nickel, but with a better stability. Platinum, first choice for manufacturing RTDs, of course. Excellent stability and reproducibility, and a theoretical temperature range from -200 to +850, and it's a guaranteed interchangeability batch to batch because of defined permitted uncertainties in the international standard. So it is, when you buy a class A sensor in Europe, it will have exactly the same properties as a class A sensor which is manufactured here in India. There is no difference.
What's the temperature range for copper and nickel?
In the old German standard for nickel resistors, the upper limit was 250 degrees centigrade. And for copper, it was the same temperature, but it was a domestic German standard. The Americans, in old ASTM tables, you will find that nickel is up to 450 and copper only up to 150 degrees centigrade.
We have a requirement in which the customer is asking for distributed temperature. For example, if you have to take the temperature of the room, so there is a RTD for the whole length of the room. So they have a winding of platinum, or what is normally used for that?
Yes, you can have this.
10 meters.
Yes, yes. It's you can use any material because room temperature. It's a question of. It's not a question of linearity. 10 meters is a question of price, basically. Yes. You can use, for example, you can use a mineral insulated cable with only one conductor inside. For example, nickel chromium, because for nickel chromium the temperature coefficient is known, and you can have it as a linear 100-meter long temperature sensor. It is possible. Yes. For resistant thermometers, there are, beside others, 8 significant parameters which needs to be specified. This is, in the first choice, the sensor material. Yes, platinum, of course, the first choice. Copper, nickel, Balco. Balco is a nickel copper cadmium alloy. Molybden is possible. Tungsten, iridium, carbon, germanium, silicon, whatever. The temperature coefficient is important. For industrial types, 0.00385. The nominal resistance at 0 degrees centigrade. In industrial application, this is mostly 100 ohm at 0 degrees centigrade. Outmost. Other applications also with high numbers, for example, in the northern countries, heat quantity measurement. Yes, when you have a big building, you have only one heating system somewhere in the cellar, and you distribute the hot water to all the flats and apartments. And so everybody has to, it's necessary to measure the heat quantity which is used, because it's a question of the price. You have to buy the oil or the gas for operating the heating system. And so every user of the flat or apartment has to pay its amount. And so for such measurements, normally PT 1000, even PT 10,000s are used, because then you can, even with longer cables, having only in two-wire technology, because the influence of the cable related to the base resistance is low and below the permitted deviation. The wiring configuration is important. Standard is 2 wires only, but the newest edition of the standard says 2-wire configuration is not permitted with class A or lower than class A. So only class B. Yes? So 3 or 4-wire configuration has to be used if you like to have a class A or refractories of class B sensors. And for, let's say, laboratory applications, a 4-wire configuration is nearly a must. The temperature range. Okay, this is depending on the application, of course. The accuracy, class A, class B, or refractions of class B. And finally, one of the final points, dimension and size. Yes? Let's say for chemical applications in the standardized protection tubes, is mostly 6 millimeters. Yes? For other applications it may be smaller. So obviously the bigger diameter is mostly longer lifetime, but the access time is obviously longer because the mass is higher. Yeah, and finally, material specifications and compatibility with the process. Of course. The newly revised 60751 with the edition of 2009. This is the latest edition. This contains also tables for the conversion of temperature to resistance, and it contains also the calendar van Dusen equitation and various test criteria, and finally also a graphic for what has to be accepted by the customer or the user from the vendor and what is not to be accepted. The latest edition is 2009, so we have obviously 2015. This is roughly 6 years, and every standard, IEC standard, has to be checked for state-of-the-art every 5 years. So the first service round has been started for this standard 60751, and okay, the German Standardization Committee is responsible for it. Sorry about. In my time, I have undersigned this standard before it becomes in force. So, but now I'm not longer, I'm only a guest in this committee. I'm not longer the head of it. So I can sit there and look and say, okay, see what happens. Okay. This is the way through the procedure. Okay. The most important change between the previous, before 9001 standard and the standard after 2009 is that now we have a clear definition or a clear range, a definition of ranges between thermometers and sensing elements. Before it was not defined. Now we have it defined. Sensing elements and thermometers. And in the sensing elements and also in the thermometers, we are subdivided between flat-form resistors and wire-wound resistors. So they have different names, F and W. Yes, and so this makes for, let's say, the relationship between vendor and user a little bit more on a practical base. Before it was floating. Yes, the vendor says, I like to have a PT100, and the manufacturer says, okay, because of price, I put a flat-form resistor inside, but the vendor expected a wire-wound resistor. And so they could not come together. There was no base for discussion. Now there is a definite base for discussion, and it is strongly recommended in the standard how to classify and how to name it for a clear relationship between vendor and user. And the second one is that the flat-form resistors have limited temperature ranges for operation, smaller than for wire-wound. Because some years ago in Germany we made a big round between nearly all vendors for the flat-form elements and about 10 users, like my previous company. And we made a lot of measurements with the flat-form elements, and we found that at temperatures below -40 and above 450 degrees, they do not follow the calendar van Dusen equitation. Only in this range. You can use it with the inside the permitted deviation, outside not. And so on an international conference we suggested to use a equitation of a higher degree than calendar van Dusen to have the same covering range for the wiring elements, for the wire-bound elements, as well as for the flat-form resistors. But there was international, we could not get an agreement to it, and so the only choice was to limit the temperature range. So I don't like it. I supported the version with a higher degree, like thermocouples. Thermocouples, you have equitation sometimes with 12 coefficients. Yes, so everybody says, okay, we have 12 coefficients. So we supposed an equitation with 5 coefficients for this, but international, there was no conclusion to it. Okay, so we have to live with it, with smaller ranges and different types. Difference is made also between resistance elements and thermometers, as I mentioned before. And a new class AA for thermometers are introduced, and it was formerly a non-standardized class 1/3 of B. Now it is included in the standard as class AA for thermometers, or class 0.1 for the W 0.1 or F 0.1 for the sensing elements. Okay, this is a table of the permitted deviations. It's valid for thermometers with a wire-wound resistor. Those with a thin film resistors have a general lower limit of -50 and an upper limit of 550 degrees, unless for class B. For class A, it is limited between -40 and 450 degrees. The reason is due to the physical construction of a flat form resistor. When you use it at temperatures below -50 and above 550, you introduce an additional error which is not be removable by annealing or another process. It's a permanent change. Yes, so since you heat a flat form resistor above 400 or 550 degrees, you have a permanent change and you drive it outside class B, for example. For us vendors, it's quite simple. If you have a complaint, we look in it, and if we monitor in our laboratory a permanent change, we can tell the customer, your complaint, let's please discuss about it. Okay, so this is what is meant in this. And this is a refractory. You see, there is a class AA. And it is limited to, the upper limit is 250 degrees. And this is a graphical display for the permitted deviations. It is only the positive side. It is exactly mirrored to the negative side. Yes? Standardized class, but it is a class which is commonly used in climatic systems like air conditioners and in automotive applications. And in the meantime, class C sensors are available up to 1,000 degrees. Each application states different requirement to the construction of the thermometer and the sensor, both. Wire-wound or metal film resistors are, depending on the application, more or less suitable. The ranges are overlapping and also the borders are floating. Wire-wound resistors means a 10 to 50 micron wire of about 60 centimeters in length is wounded, coiled to a coil, and then inserted into two bores of a capillary, a ceramic capillary tube. So each half of the 100 ohm is in one capillary and then connected, and the second one. The capillary is then filmed with a kind of glass and is sintered afterwards to fix the wire coil, but not 100%. This is not possible. Nevertheless, a resistor is sensitive to vibrations. And according to the 6075, it must be withstand in the range of 5 to 500 hertz, only 20 to 30 meters per second square, means 2 to 3 G. This sounds quite much, but we have done a lot of measurements for vibrations, and we seldom found vibrations within this range. In most of the industrial applications, the vibrations are much higher, much. Your body, your human body, is very less sensitive to vibrations. Yes, this is by nature, because if you were sensitive to vibrations, you would be disturbed anywhere. Yes, so when you touch a pipe or you touch a motor, you feel a little bit that there is a vibration, yet you have no measurement how much. And as higher the frequency, the amplitude becomes smaller and smaller. It is like the ohmic value, the ohmic law. Yes, higher frequencies have, with the same acceleration, smaller amplitudes. Yes, so if the frequency is high enough, let's say in the range of 5 kilohertz, or even 10 or more, which is typical in power applications, in the steam line, you have only amplitudes in the range of microns, but you have accelerations in the range of 30, 50, and more G. And this is quite not good for RTDs. So in some cases, you have to use thermocouples instead of RTDs, even in steam lines in power stations. We found some places where it was impossible to measure with an RTD at this point, because the vibrations due to turbulences inside the steam line did not allow it. We had lifetimes of hours for such thermometers. And we made measurements, and we found sometimes measurements when outside the boiler is a position where the pressure is fine adjusted, and they do it by spraying water into the steam to lower the temperature, and therefore they adjust the pressure. And you spray water, cold water, into a steam of 550 degrees. So everybody thinks it will immediately go to steam, but it doesn't. It remains in droplets. And the droplets come with about 100 meters per second to the sensing element, to the protection tube of the sensing element. So small droplets at 100 meters per second, they cause vibrations, I can tell you. We have measured vibrations up to 300 G. This is impossible for an RTD to withstand. It is definitely not possible. And at frequencies of 10 kilohertz and above. Okay, wire-wound resistors are only limited resistant against temperature shocks. It is due to the different linear expression coefficients between the platinum wire and the ceramic for the capillary rod. Glass sensors are basically wire-wound resistors. They are nearly immune against vibrations and temperature shocks, especially in cryogenic applications. Disadvantages is hysteresis and the limited operation temperature range. So this is the principal construction of a wire-wound resistor. Yes, you have a 2 or 4 bore ceramic, and the helical coil of the 100 ohm is divided in 2 parts, and it is connected on the opposite side of the connection wires. And during the process, you can pull out a little bit the wire and re-weld it, and so you can adjust the resistance quite fine. But basically, it is not possible for a wire-wound resistor to produce class A. It is not possible. You can produce it nearly, and then afterwards you have selected. Yes? Now processes are available where you have 65-70% class A within class B. This is now possible, but for a flat form element you can have about 98% class A to class B. Yes? This is a principle how to produce a glass resistor. It is a glass rod where the PT wire is wound on, and then it is covered with a small piece of glass pipe with a different material, and then it is heated up, and so the outer glass rod is molten down to the inner glass rod, which has the platinum wire, so the platinum wire is really fixed inside the glass. Very advantageous. Disadvantage is glass and platinum have different linear expansion coefficients, and therefore you have hysteresis and all the other effects. So metal films resistors are constructed by printing or sputtering a thin platinum layer to a ceramic wafer. Honestly, in our times, this kind of sensors contain nearly none platinum. Most of it is molybdenum, alloyed by indium and other agrees, which the vendor does not tell you. So only the outside effect is the behavior of a platinum resistor, although it contains only some small number of percentage of platinum. Now, most of it is only an extremely thin layer on the wafer to act as an interface between the ceramic and the real sensing element. Therefore, the platinum normally is used only. Otherwise, a price of somewhat around less than $1 is not possible, even not in big quantities. Yes, where wire-bound resistors start at least at $5 each, probably $3, but this is a normal price for it. There's a difference in the thickness of the layer. 10 to 15 microns is a thick film, and 1 to 2 microns is a thin film technology. In our times, only thin film technology is used. Thick film is not longer used. And the width of the wire is approximately 7 to 30 microns. And the resistor, normally it is on the surface, and then with a laser, the meander form sensing element is trimmed to the desired value. And this can be done. You have wafers in a size like this with hundreds of elements on it, and you can put it on a cooled plate, adjust it to 0 degree, and so you can really make a class A resistor online. This is possible. This is the biggest advantage for the flat film resisting elements. Yes? So you are sure that probably somewhere in the edges you have some elements which are non-class A. Metal film resistors reach nearly to the temperature properties of wire-wound resistors. However, hysteresis and drift above 500 degrees is significantly poorer, means you have a permanent change in the properties. It's a faster response time because the heat transfer coefficient between the base material, between the wafer and the sputtered material is much better as in a capillary rod where you have glass as an additional interface. The resistivity is much better against vibrations, and the resistivity against temperature shocks is also much higher. It is possible to take a sensing element from 400 degrees and put it in water without changing its properties. With a wire-wound resistor, it is not possible. We like everybody who does it. Oh, sorry, I'm not a sales engineer. Smaller temperature sensitive lengths. You can construct it smaller. Wire-wound elements are available. The smallest one is 0.5 millimeter in diameter and 15 millimeters long. It is available from a company in Korea, $70 each. The price decreases with the dimension, of course, yes. Bigger elements are less, but the price limit is very small. Flat foam elements are available at present at a reasonable price, 0.5 millimeters wide, 5 millimeters long, and 0.5 millimeter thick. So you can construct a mineral insulated RTD with 1 millimeter outside diameter. And a fast response time and good properties in Class A at a reasonable price. It is possible. So this is an imaging of the flat foam element. In the background, you see what is called wire. And you see on the edge of it, you see that how it is laser trimmed. You see the different shots. Yes? And the meander is seen in the upper right corner with the two lead wires attached to it, and afterwards the entire surface is covered with a kind of glass to protect it from the atmospheric and the ambient conditions, with a little bit more like a small hill on it in the area where the two lead wires are connected. So this is the element in the lower left side, what you get when you buy only the sensing element, or the vendor when he buys it, the producer when he buys it from its vendor. And they are available in a lot of forms. They are standardized forms, yes. For example, 2 millimeters wide, 10 millimeters long. This is a standard form, but they are available in a lot of different forms. So this is an imaging about wire wound. The upper two are wire wound resistors, and the lower one is a flat foam resistor. And you see the dimensions. And for the lower one, for example, the sensing portion is only 0.6 times 1 millimeter. So it nearly is sensitive like a point, very close to a thermocouple. Yes? The above is 15 millimeters long, 0.9 millimeter in diameter, and the sensitive length is 12 millimeter. So it integrates a temperature profile above this 12 millimeters, obviously. At present, in normal applications up to, let's say, 400 degrees, the metal film resistors are used 95%. Due to the price, wire wound resistors are quite seldom in use. To have the same appearance and handling of the elements, the metal film resistors are potted into a small pipe. The ceramic tube protects the sensitive surface again, and the resistivity against drift due to contamination increases, but on the other hand, the price increases as well as the response time. And the response time is normally one of the advantages of a flat film resistor. And also the self-heating is higher due to the excitation current as in comparable flat form resistors. So how is this? Is how it looks like. How to measure? To measure a resistance, an excitation current is needed. We are in the DC world here, and the ohmic law is in fact. So what you have on the left-hand side, RT, is the platinum resistor, which is sensitive for the temperature. Then you have two line resistances in this two-line configuration. You have two contact resistances where you connect your wire to your meter, and so all these 5 resistors are connected in row and have an effect on the result, obviously, because you drive a constant current, mainly 1 milliampere for meters. For transmitters, you are normally in the range 0.8, 0.5, even 0.3 milliampere. Yes, and so you measure basically the drop, the voltage drop at the input terminals of your meter. This is what you basically measure. You cannot measure, except you use a bridge, you cannot measure a resistance directly. You always use a current and you measure the voltage drop. Okay, so you see all these 4 additional elements or resistors have an effect on the accuracy of your measurement. And so you can see that for longer resistant thermometers or longer copper wires, it is not possible to achieve a class A system. It's definitely not possible. Yes, the resistance of the wire, even when you have 1.5 square millimeter, if the wire is 10 meters long, you drive definitely the system out of class A. You are only in class B. And in addition, copper has a temperature coefficient close to platinum, a little bit higher. So the line also is a temperature sensor in itself. And at elevated temperatures, you increase the line resistance in addition. You have to take this in account when you design your measurement cycle. The advantage is low-cost installation, only 2 wires. Disadvantage, wire and contact resistors have a direct influence on the measuring result. And it is not suitable, basically not allowed in the newest edition of the international standard for class A or better circuits. So this is an example for the loop resistance for mineral insulated cable with 4, 6 or 8 conductors and an outer diameter in millimeter. So for example, 6 millimeter, it's a third, you see, where yes, 6 conductors with copper in a 6 millimeter outside MA cable, and it has a resistance for each wire of 75 milliohm, and the influence for these 2 wire systems on a PT100 at 0 degrees is 200 millikelvin or 0.2 degrees centigrade per meter. Yes, so if you have only a resistant thermometer 250 millimeters long, it might be acceptable. But if you have a resistance thermometer of 1 meter or even 1.5 meter, this is not acceptable because it directly drives you outside class A. This is the reason why. And if you have smaller diameters and therefore you have smaller areas for each of the conductors, it raises up. For example, 4 conductors in an MI cable, 1 millimeter outside diameter gives you an offset of 8 Kelvin or 8 degrees centigrade per meter. This is a number. You can also take a wet sump and try to measure the temperature. It has the same accuracy. Okay, the same happens with the copper lead wire, of course. Not only with the mineral cable, but also with the copper lead wire. Yes, and to reduce the influence, you have to increase the cross-sectional area. Means you have more copper, and at present copper is quite expensive. Yes, a ton of copper is some $1,000 at present. So the reducing, or you think by reducing only to 2 wires and you increase the cross-sectional area, comes nearly at present to the same price. So it makes it not very attractive to use it. So the best choice in industrial application is this 3-wire circuitry. Yes, the meter is a little bit more, has some more coefficient because it needs 2 current sources which are as equal as possible. Yes, and so you have 2 different loops. One loop containing the lower, containing the contact resistances and the line resistances, as well as a temperature sensitive platinum element, and the upper one contains nearly the same except the temperature sensitive element. And if you could take in consideration that all the contact resistances and the line resistances are equal, yes, then you can take the voltage drop in the lower cycle minus the voltage drop in the upper cycle, and the result is only the voltage drop by the temperature sensing element. This is true as long as the failure resistances are equal, but in practical it is not. You can eliminate about 90% of the influence, but not 100%. This is not possible. Even the cable manufacturer is not able to take care that in his multi-core cable all the meter resistances are definitely equal. It's not possible by price and afford. So about 90% of the influences may be covered by this configuration. This is possible, and the instrument is normally significantly more expensive because of the more components which are inside, but it is widely used. Yeah, for laboratory applications, everybody knows 4-wire configuration, the best choice. You have only one current source. You see it on the inner cycle. You have the line resistances and the contact resistances. And you have a different loop from it. It's the outer loop, or have also line resistances and contact resistances, and you measure the voltage in the outer loop. The advantage is that your voltage to digital converter or your input amplifier has an extremely high input resistance, typically 10 to the power of 12 or higher in ohm. Yes, so that in the outer loop you have the voltage drop of the measuring resistor. 1 milliampere at 0 degrees means 100 millivolt. It's the driving voltage across an input resistors of 10 to the power of 12 or even higher. So this means the current in the outer measuring loop is in the order of picoampere or below. And so the voltage drop on the low resistances, line resistances and contact resistances are not longer significant and are so low that you have not to take them in consideration in your uncertainty budget. This is the sense of a 4-wire technology and why it is used in laboratory applications. Okay. Yes, complete compensation of all wire and contact resistances regardless of the cross-sectional area means the AWG number of the wires. Disadvantage, slightly higher installation costs. Okay, this is how it's a principal picture, how it is internal made. You see, you have probably a kind of protection tube or mineral insulated cable. You have an insulation rod inside for the copper wires, and you have the connection points between the platinum sensing element and the copper wires, and then you protect it with a cap or with a small pipe and a bottom, and you fill it with insulating material, mostly an aluminum oxide powder. This is the principle for 3 wires. 2 or 4 wire follow the same principle. And in case of platinum resistors, which have platinum lead wires, besides the sensitivity against vibration for the sensing element itself, there is a second weak point at the welding of the platinum wire to the copper wire, because it is a melting process. And the copper makes the platinum extremely brittle. It causes a coarse grain. And so this transition point is also very sensitive to vibration. So available are lead wires for the sensing element, which is a nickel core covered by a thin platinum surface. And so it is good for the connection between the nickel and the copper, which they form a stable alloy with a fine grain, and so it is not so sensitive. Okay, these are mainly the constructions you know. On the right side, the lower one is a typical European construction for the steam lines in power stations. The cylindrical, only the conical part looks into the steam line, into the steam. The cylindrical part is inside the wall thickness and is a part of the welding structure. And so then you have an extension pipe for the insulation material. The next one on the right side, the middle one, is a typical construction for chemical industry. Yes, mostly the thread is ½ inch, and the upper one is general purpose, and the lower one of the left side is the measuring insert, which is used in the 2 constructions on the right side, the lower ones. And the upper ones are for general purpose, machinery, automotive, whatever. Okay, we have some special sensors for very low deep temperatures, but I saw from the list that here is nobody which really deals with very deep temperature. Or is there anybody who has with liquid gases, liquid natural gas or something like this? Nobody? Okay. Then it is only for small informations that for the temperatures below the hydrogen triple point means 13.8 Kelvin, there are also resistance sensors are available. Okay. For?
For higher vibration applications like fans and values of fans and
Yeah, the first choice would be a flat film resistor. Yes, but the temperature range is limited to, let's say, maximum 450 degrees. And the construction must be in accordance. So the inner construction of the sensor or the measuring insert must be in accordance to your requirement. And what do you mean with higher frequencies?
vibration in the tune of like 10 mm per second.
Yes. So this must be carefully discussed between user and vendor, because also the inner construction of the sensor must be in accordance to the requirements for vibrations. Probably you have to put in damping elements. You fill it with silicon grease or something like this. Yes. Or use potted resistors and you construct it in a mineral cable and afterwards you squeeze it again to have better inner or lower inner tolerances or so. But it's not easy, I can tell you, and you need to discuss it really very intensive with your vendor. And the vendor, you must select that he knows how to do it.
Frequency is quite high. Failure of RTD, perhaps even for very vibration, frequency of failure is quite high. Sometimes normally
Yeah. Yes. Normally you have a break. Yes, and yes, yes. But you can do something against this by choosing the right materials. And keep in mind, in vibration, it is a kind of Ohmian law. Yes, so frequency, amplitude, and acceleration are tied together in a firm law. Yes, so to say we have high vibration can also mean such amplitude, but only 0.01 hertz. Yes, a pendular at a clock is also a vibration. Yes, so the interested range starts somewhere at 1000 hertz, and then 5 or even more G in acceleration. This is exciting. Okay, somebody else?
Not a query, but I'd like to thank for clarifying the prolonging load from past 13 years, wherein in diesel generators, which are being used, they are using Detector thermometers.
They are using Detector.
We are using Detector thermometers for a temperature range of 300 to 400 degrees. I had a long query in my mind, why can't we use for RTDs? I got the answer. Thanks.
Okay.